Hi everyone, today I'm going to share a paper named EEG Simple Con Deep Learning Baseline for BCI Motor Imagery Decoding. I'm going to talk about the auto introduction, proposed method, evaluation step, result and discussion and conclusion of this paper. About the author, the main author of this paper is Yassin Al-Awhidin. He's graduate in IMT Atlantic in Paris in 2025. He leads a team to research in field of BCI, deep learning, and EEG. Next, I'm going to talk about the research background. Brain-computer interface have gained significant research attention. Motor imagery is particularly important due to its potential social and medical impact, such as supporting assistive technology or post-stroke motor rehabilitation. Moreover, deep learning method promise to integrate feature extraction and classification into a single step. They hold potential for generalization across several subjects by exploiting multi-subject dataset. But the BCI now is currently facing some limitation. Current BCI systems suffer from poor reliability, require long calibration time for each subject or section, and have limited generalization capability. These limitations stem from the noise, non-stationary nature of EEG signal, and significant inter-subject variation. In addition, deep learning models also often suffer from high computational requirement, complexity, long calibration time, and lack of clarity regarding architectural choice, making rigorous benchmarking difficult. Because of the limitation, the author has proposed a EEG Simple Con. It is a deep learning model. Let's look into the architecture of this deep learning model. The model is designed composed only standard layer including 1D convolution, batch normalization, value activation function, and max pooling function. It stacks plenty of small 1D convolutional filter to increase the receptive field and capture the intricate pattern. Max pooling is used for temporal downsampling, and the number of feature mapped is increased by square root 2 to compensate for the dimension reduction. Third one, the final layer average will average the signal over time, making the full architecture invariant to temporal shift of its input. This simple architecture ensures low computational demands and is easily understood. The figure below is EEG Simple Con architecture. Next, going to talk about the key routine ingredient during training. The first step is pre-processing. Adopt minimalist approach using only simple 0.5 Hz high-pass filter and resampling, allowing the model to automatically learn relevant feature. The second technique is normalization technique. It will use the Euclidean alignment. Project data into a domain invariant space based on the covariance matrix to address the distribution variation across different subject and section. Second, session statistic. Normalization is performed using session statistic instead of subject statistic to account for variation between recording sections. The third one is batch normalization. During evaluation, batch normalization statistics are recomputed directly from the test set data to incorporate personalized user-specific statistics. This enhances adaptation but cannot be used in online scenarios as described. For standardization, transform data into a meaning of 0 and standard deviation of 1. It scales the data across subject and session and is performed to ensure these properties are maintained. The last technique is regularization technique. Authors have used mix-up, a powerful data augmentation technique that generates synthetic training example by linearly interpolating input and corresponding losses. It is necessary for EEG synchrotron to strongly regularize and prevent overfitting because of the model contains a relative high number of parameters. Second, subject-wise regularization. Adding a classification head to identify the subject aimed at helping the model understand inter-subject variation. Now we're going to talk about the evaluation step for this paper. Evaluation was conducted on 4 open source motor imagery datasets, chosen for their frequent use and difference in size and recording setup, ensuring a comprehensive assessment of generalizability. Author has made 3 types of assessment for this deep learning model. The first one, within subject, training and testing on different parts of the same subject data. The second, cross-subject, training on data from all subjects except one and testing on the data of the left-out subject. This is the primary method for measuring generalization ability. The last one, cross-subject with fine-tuning. This model is pre-trained on all other subjects, then fine-tuned on a calibration part of the target subject's data, and finally tested on the remainder. This reflects a realistic usage scenario where a pretend network is adapted to a new user. And the result is significant. The overall performance, the EEG synchrotron is at least as effective or far more efficient in classification performance compared to. Let's take a look of the result of the EEG synchrotron. Overall, EEG synchrotron is at least as effective or far more efficient in classification performance compared to other state-of-the-art model. In the cross-subject with fine-tuning setup, EEG synchrotron is particularly show a real progress and significantly outperform other literature models. Third one is transfer learning benefit. EEG synchrotron has proved that transfer learning yields a noticeable gain of approximately 8% accuracy on the BCI dataset, especially benefiting subjects that are difficult to classify. The last one, EEG synchrotron demonstrates a low latency and competitive inference time, making it practical for real-time application. The within subject configuration has lower latency than EEG-net, despite having 60 times more parameters, challenging the conventional assumption that fewer parameters guarantee better latency. Low latency is achieved by simplifying the architecture. The key finding of this paper is the batch normalization tricks and mix-up are the two most effective elements in the training routine. Removing all normalization elements results in a significant average accuracy loss of 7%. However, this loss is much smaller for a large dataset, around 2.5% drop, than a small dataset, 12% drop, suggesting that the pre-training on large dataset could enhance online generalization. The last is subject-wise regularization has little to no effect. Let's go to a conclusion of this paper. This paper introduced EEG SimpleCon, a simple yet competitive deep learning model, demonstrating that using standard and simple components can achieve state-of-the-art motor imagery decoding performance. The result questioned the needs for ad hoc deep learning architectures specifically designed for motor imagery decoding tasks. Third, transfer learning calibration show very promising result in online evaluation setup, outperforming standard motor imagery approach. The contribution of this paper is the author shared the code to reproduce all experiments, intending for EEG SimpleCon to become a new reliability baseline for the BCI community. That's all for my sharing. Thank you.